Okay, last class we were talking about esters. They're kind of interesting. Quick revision is that an ester will form like this. You need an acid. With an alcohol. One, two, three, four, five, six. And if you recall, the OH from the acid and the hydrogen from the alcohol join together to form water. And the rest of the molecule joins together to form an ester. Pretty easy. Now this is kind of important. I'm missing an O. This is kind of important. It looks pretty simple. It's important in two ways. Well, it looks deceivingly simple, but if I give you an ester and if I ask you, what is it made of? People can get easily confused because it just looks so simple. You can figure it out, but people will get confused. The other thing is esters go on to the next chapter where they polymerize. So it's really important to kind of pay attention to little details. One such little detail is, well, the OH from the acid and the H from the alcohol come out. If you know this, and the other part, if you can successfully recognize an ester link without any confusion, you can move on to polymers, right? But before that, let's try naming this. We already know what this is made of, but let's say this came in the question. And the question was, what is the name of this compound? Name it. Well, the naming convention for an ester is, or the system is, it's something, the name is something "ile" and then something "know it." That's any ester's name. What is an "ile" over here? Well, the "ile" comes from the alcohol's name that is used to make the ester you're talking about. Because any ester is made up of an alcohol and an acid, right? Carboxylic acid. So the name of the alcohol comes over here, but it has a twist. It turns into an "ile," the name, and the acid comes over here. Right? So let's look at, we already know what this is made of. So how would you do this? So if this molecule is given to you, you know it's an ester, and they ask you to name it. First thing you do is identify the ester link. I'm like, oh, here's my ester link. All right. So let's cut the ester link where it joined. Where did it join? It bonded over here. This is the new bond created between carbon and oxygen. This is how they're joined together. So what do? You divide it up. You up. All right. Now, once you cut it up, you have to successfully identify which part came from the acid, which part came from the alcohol. Now, the carbon with the double bonded O, this side of the molecule can only come from the acid. So you know this came from the acid and this came from the alcohol because it doesn't have a carbon with a double bond. What was the original name of this molecule? This was ethanoic acid. And this was ethanol because, you know, 2 carbons each. So this name would go over there on the left. And this name would go over to the right. So what would it be? It'll turn into ethyl ethanoate. Does that make sense? Thumbs up if everyone agrees. Right? Pretty easy, pretty straightforward. Naman, you're horribly late. You're 10 minutes late. Anyway, okay. So let's do a question. What is this molecule called? You can drop a message in the chat if you know what it's called. Some people might find it very easy. To one point, you just look at it and you realize that, oh, what it's called. Like it becomes very easy. But if you're starting out, you should cut it up. What could happen is the molecule can be given to you in a very, very confusing manner, right? So one person got it. Ira, how about you? Naman? Any idea how to name it? Yes or no? I'll wait for a bit. Do we know or no? Noman, any idea? Are you working it out? No clue. Okay. And Era, any idea how to do it? Propyl methanoid. Okay, you got it. Take it. Resuming, and you guys see it is propyl methanoid. How did I get it? Now the steps were, I'll repeat because somebody was late, is you identify the ester link. You cut up where the ester link was formed, where the bond was made, where the carbon oxygen bond was made, right? You cut it up and you identify what the acid part is, what the alcohol part is. Well, if you're worried what the acid part is, this is it because it has the carbon with the oxygen double bonded. So this is methanoic acid. And this is the alcohol, which is propanol. Now, any ester's name is some alcohol name, but they turn it into an aryl, and some acid name, but they turn it into a noate. So you see methanoid is going here and propyl is going over here. So it's propyl methanoid. No, acid won't be the first part. So let's try another question out. And hopefully we can be a little faster. And that's the confusing part. They can really mess it up for you. They might not even give it to you in a straight line. We'll do some questions right now after this past paper questions, and we'll try to name random molecules. And it'll be good practice. You know, something like this. Oh yeah, it is Christmas. Is it Christmas today? No. Tomorrow. So yeah, so we've been writing the acid first because it just looks nicer to me. We're kind of used to it. But if we try to do this, you'll realize it. Now you already know, now Kawal already asked, hey, will the acid part be first? So obviously I changed it. So you know exactly what to expect. The challenge becomes that, if you have like 3 random questions or like when you're doing a paper, you're just not ready for it and it shows up and you're like, oh, whatever. And just people mess it up. So it's pretty systematic. Yeah. You identify the ester link, cut it up, find the acid, find the alcohol, and then name it. So ethyl propanoate. Yeah, I think so. This is the alcohol part, which is ethanol. Propanoic was it? So they'll join to form ethyl propanoate. Right? And those who are confused, this is the ester link. They joined over here, so I cut it up. Of course, this is the acid part. I called it propanoic. This is the alcohol part. I called it ethanol. Right? Pretty easy. Well, not basically, yeah. Like that's fact. The carbon with the, this part of the molecule came from the acid, right? Like, how else did it get there? Nothing else in your organic series has a carbon oxygen double bond. So it's easy to identify. So let's use that as help. Right? Makes sense? Easy? Yeah. Easy peasy. Pretty good. Yeah. All right. Let's move on. All right. So we'll do just a bit of polymers over here because we're already on esters. So we already saw how ethene or alkenes can make polymers. So here are some polymers that esters can make. Now, this is where you really want to see a molecule of alcohol and an acid as a Lego piece, quite literally. Now, this could happen in multiple ways. Essentially, what's happening is the alcohol functional group can easily join with an acid functional group and form an ester. You already know this, but it also ends up joining the molecule. So let's say you had a molecule like this. I'll make it extra small so it's easy to repeat because we're going to make a long chain. Yeah. And let's do that. This is our acid. I'm really making it very close to the heading. And then we'll have our alcohol. Right. Let's just give it some space, some room to breathe. This is an acid on the left-hand side, and this is an alcohol. Ethyl ethanoate ban jayega. Pretty, nothing spectacular. What if I change my acid like this? I give both carbons the functional group. And I change my alcohol where it has both sides as a functional group. So what's going to happen is, well, the first thing that's going to happen is you already know. Now, don't worry about naming this because we don't need to, but this part and this part can form an ester. Why? Because an alcohol and an ester can esterify or form an ester link. So let's do that. This molecule will pair up with this molecule. Like that. Right? Essentially, I made a mistake, didn't I? Sorry, like that. Right? And what could happen is, so they're not two molecules in the entire world that are, reacting together. If you put like some alcohol solution and an acid solution joined together, so they're like millions of molecules. What could happen is, can't another acid molecule eventually, after this ester is formed on the left, can this molecule show up over here like that? And if it does, it has the same conditions to, esterify. Look, this is the acid part. This is the alcohol part. Can they join? Yeah, why not? What can stop them from joining? Right? So they will join. So let's remove that. And now they've joined. And what you see is, we started off with an alcohol that joined to an acid. Now, another alcohol has joined to it. And you can quickly see there might just not be any limit to this. Why? Well, what if in that millions of molecule soup, another molecule of an alcohol shows up? Like that. What do you guys think? Will this pair up? Can this pair up? Alcohol, acid function group. What's stopping it? It will pair up. And this could keep on going forever and ever and ever. Right? So let me just show you how complicated it looks if I actually do that. I'll have to make it smaller, but it looks kind of cool as well. This is a long chain of esters. Many esters joined together. What would we call this? A polyester. You've heard of polyesters before? A lot of people, they make fabrics out of it. Like some clothes you wear, bags are made of polyester. Yeah, so this is how polyester is made. They literally take an acid, alcohol, heat it together. They form a long chain of polyester, and you take it out, you turn it into clothes or whatever you need from it. The problem over here is it's not complicated. It just looks really complicated. So what you can do is, and a lot of people making or standardizing chemistry also agree. So what they do is they say, well, this part of the molecule doesn't really help you, and neither does this. So what they do is they end up making blocks out of it. So a lot of times what you'll see is they won't care about the molecule that's in the center, so they'll make it like this. And we started with ethyl ethanoate, right? Ethanoic acid, this looks wrong. Oh my God, why? One of these days. All right. So what they try to do is make an acid. And they say, we don't care about the part that's not the functional group. So they make like a big purple, well, not purple. They can choose the color, but like just a big box. And they'll just put the functional groups on them like that. And for the alcohol, they'll do the same thing. Remember, the functional group for an alcohol is just the OH, right? So they'll make it like this. So what could happen is, essentially, you could have anything in the box. What is this box? It could be just one carbon, one CH, or it could be something longer, like this. The problem with it is if they start showing this, people might get confused because it is just so much over here. How do you process it? So what they end up doing is they put them into rectangles and they only show the functional groups. So what would this molecule look like if it esterifies or polymerizes? Or what is the difference between an alkene polymerizing and this polymerizing? Well, you tell me. Isn't it a completely... Polymerization is just the process of a molecule making a bigger molecule by repeating itself, or to the most part repeating itself. Don't you think there's a major difference in the polymerization of this because it's done through esterification, whereas that one is done through the double bond opening up? So, now, I don't know if you guys agree or disagree, but this molecule or this, oops, we'll copy this. To some, this might look a lot simpler than what's drawn up, right? Do you guys agree or disagree? Does this look simple or not? I'm in a position where I'm okay with this. I'm in a position I'm also okay with this. What do you guys think? Is this a simpler way of expressing it, or is this a simpler way of expressing it? It does have two functional groups involved. So you can, yeah, it's kind of like, yeah. But you can say, like, that doesn't really make any sense, Kaval. Polymerization through esterification. Like if you say two functional groups are involved, you can say two different molecules are involved, right? You can keep on going any, like, oh, alcohol and acid are involved, whereas in the other one, only alkenes are involved. You can keep on making, you can do this like in paper, but in the paper, they might do it like this. So they'll just show you a molecule like this, right? So I'm just saying the top diagram and the bottom diagram literally has no difference in them. You know, like if we, it's just a black box. It's just like they hide, they're literally censoring the ugly part of the molecule. Yeah, but it's difficult to censor because these are literally the functional groups. So, but if this molecule looked very complicated, and it can look very complicated, like, you know, like maybe it just had a lot of carbons, then it would really, you know, suck to draw this out. Like an acid, if you had to draw like 3 repeating units or something like that, This would be really annoying to draw. So they normally show a black box when it starts getting complicated. But the point is, you should know that there's no difference between this and this. The other thing is, if this comes up or this comes up, you treat it the exact same way. That's kind of it. All right. So Kamal's asking for some differences between polymerization. So the last one we did was addition polymerization, if you remember. It's called addition polymerization. Where an alkene can open up like that. That's a repeat unit with one bond missing. I'll repeat it. One key difference I would say is there's no other product. It's only one molecule formed when addition polymerization happens. Can addition polymerization happen between two different alkenes? Absolutely. Who's stopping them? But generally they won't talk about it because then it really gets complicated. So for in our world, it's only one alkene that's generally used. The other sort of polymerization, this one, get a nice part of the molecule. This is formed through esterification, and this is called condensation polymerization. Condensation is just a cheating word. Condensation means, like condensation. I guess you guys know what condensation means. It's called condensation, when you have like a very cold glass of water and there's like water forming all around it because it sticks to it, right? That's called condensation. So what happens is when you do this reaction in a beaker, a lot of water is formed. Remember, because H2 is formed every time an esterification happens. If this is formed, that water shows up all around the beaker, right? When you're forming it in a beaker. So condensation appears. So they just called it condensation polymerization. Why is this all the way to the left? Right? So condensation polymerization strictly refers to the polymerization between alcohols and acids, whereas addition strictly refers to the carbon-carbon double bonded polymerization. Sorry, addition is carbon-carbon double bond polymerization because there's no water formed. They're just being added together. There's nothing else. There's plus nothing, right? It just turns into one thing. And that by nature is called addition. Okay, pretty easy. And that's kind of marks the end of organic for us. And we've already kind of started polymerization. Is this easy for everyone? Can we move on to doing questions now? What do you guys think? Pretty easy. So let's do a bit of alcohol questions, then acid questions, then move our way backwards, because the most recent thing we've done is alcohols and acids. So let's see if that can work out. Or actually, let's start with acids and go backwards. Noman, Era, any question? You guys have been very quiet, Era especially. I copied it like 4 times, it didn't show up. It is kind of strange why it just won't show up. There we go. Everyone has a link for this. I think I spammed it to everyone. So yeah. It's an 80-page workbook. Is it 80? It's pretty long, 91 pages of questions, pretty comprehensive. Has answers as well. Alcohols, carboxylic acids. All right, a liquid reacts with each of sodium carbonate, potassium hydroxide, and ethanol. Right, pretty cool. What is this liquid? So this is a chemistry question. Well, it seems to me that a carbonate can readily react with an acid, and potassium hydroxide is a base. So an acid can easily react over here for these two. What reacts with ethanol? Nothing really, aside from a carboxylic acid that can esterify with it. So we do have a carboxylic acid in the response. Take B, pretty easy. People, if you can answer in the chat, try doing it. Let's try question number 2. Four compounds are shown. Which pair of compounds have the same empirical formula? You guys know what empirical formula is? Empirical formula highlights the ratios. Right? So to find page number is, sorry, 37. We're on page number 37. So empirical formula, to find the empirical formula, you really need to know the number of each atom. So let's try with the first one. I'm just deciding on what color to use. I really don't want to use pink today. Let's go with orange. You have carbon, hydrogen, oxygen. So for the first one, how many of each do you have? You have 4.
8 hydrogen, 4 carbon, 2 oxygen.
I'll ask you to mute because there's a lot of noise. Ahmed, there's a lot of noise on your end, man. Ahmed, don't unmute yourself. There's a lot of noise. You have, okay, that's weird. How is that possible? How do you have 2 prints of, how could that happen? We have the same worksheet. I don't know. Let me check. But yeah, all right. That's extremely unlikely. I want to check this right now. How could you have 2 pages? No, I think whatever you have, try downloading it again, because I think while moving the pages, you ended up copy pasting the pages. Oh, you took out double prints. Oh, lol, Lamar. Oh, I can't. 4 over here. That's just funny. 2 over here. 1, 2. It's not funny. Printing just is hard. 1, 2, 3, 4, 5, 6, 7, 8. 8 over here. So the molecular formula is C4H8O2. That can be simplified as to C2H4O, right? Let's do this a little faster for the next one. It's C3H6O. This can be simplified. C2H4O. That can be simplified. So essentially, one oxygen is telling you it can be simplified, so it's a big help. This one is C2H4O2, which is CH2O. Right? So which one is the same? Same empirical formula. Yeah, I think this is this one and this one, right? 1 and 3. Yeah, pretty easy. All right, let's try naming each of these esters for practice, because the question itself is like horrible. Pretty easy, just a waste of time. Question number 2. I like how the label's below the question. It's kind of annoying. It's all right. It's just one question. You can change the page later. Let's name this ester first. What is this ester called, though, number 1? So you can see all of a sudden, if it's drawn, typed out, it just looks a little more difficult. The first one is ethyl ethanoate. You cut it off here, acid, that's ethanoate. This is ethyl ethanoate. What about this one? This is not an ester because it doesn't have a carbon oxygen bond. This is not here. This is also not an ester. This is an ester? Not really. It's an acid. It is ethanoic acid. Right? You don't have to worry about naming this or this because they're not in the syllabus to name. Take it. What's that big orange line in the middle? Huh. Do you guys see a big like orange mark in the middle? Yeah, why is that there? Sorry, give me a second. Now it's gone, I think. A liquid reacts with each sodium carbonate. It's the same question. Let's do some actual questions. Question number 8. Organic compound X has a molecular formula, blah, blah, blah. Turns damn blue litmus paper red. What is the structure of X? What of these 4 can turn damp litmus paper red? Has to be an acid. Which of these are acids? Then we can find out the molecular formula. The answer is D, because A, B, and C are esters. Quick ester naming check. This is methyl propanoid. This is ethyl ethanoid, so I won't name it. This is propyl ethanoid. Sorry, methanoid. And this is butanoic acid. Pretty cool. Yeah, shall we move on? I'm moving on. The diagram shows the structure of oxalic acid. Which alcohol is oxidized to form oxalic acid? What do you guys think? This is oxalic acid. So we don't have to worry about naming it. Any molecule that has multiple functional groups, you don't have to worry about naming it. Which alcohol will oxidize? Alcohols can easily oxidize. So the carbon carrying the OH group turns into this. Because this has two acids, functional groups, it can only be C that can turn into oxalic acid, because both of this will turn into an acid-acid functional group, right? Just for fun, we can name these compounds. You know this as ethanol. Looks a little different because the OH bond is shown. For our IGCSE friends, this is known as propan-2-ol. This is for IGCSE people only. For Cambridge people, that's all right. You don't even have to bother with naming something like this, but it's propanol to you. This is, ethan dioic, but no one cares. You don't have to worry about naming it. This is some butan dioic sort of thing. It's all right. You don't have to know how to name this. But only IGCSE people should know the name of this compound. All right, let's move on. Two equations involving ethanol are shown. Ethanol can react with oxygen under oxidation, can undergo oxidation to form an acid. Glucose can be fermented to ethanol and carbon dioxide. Sure. All right, what are the molecular formulas for row 1 and row 2? So which carboxylic acid will be formed? Over here, it'll be ethanoic acid. Ethanoic, right? So which of these is ethanoic? I think this is ethanoic, this is ethanoic. All right. What do we need a catalyst in? Ethanol plus what's the catalyst over here for ethanol reacting with oxygen? The reagent you use is KMnO4. So you don't really need a catalyst. Over here, you need yeast. Yeah. So for 2, I think you need it. Technically, that's the catalyst. Yeast has enzymes that will catalyze the reaction. Yeah, I'm not too sure about this. My memory is not working too well. Yeah, so I'm not going to answer this. I'll just leave it in the comments under the video after confirming. But I'm very sure it's this, but I'll just say comment. Check comments once. Right? Because I'm not too sure. Do people have like an opinion over here? Yeah, because you need acidified KMnO4. So I'm confusing my A levels a bit to my O levels. That's kind of always annoying. But I think it's just over here. They're calling yeast as a catalyst. But let me move on now. 16, I want to skip. I think we're done. Yeah, what's the answer for 14? Yeah, it's C, right? But I'll just confirm it anyway in the comments. All right, let's move on to alcohols. Question 1, the structure formula for some organic compounds are shown below. Which compounds are alcohols? Pretty easy. I expect who to answer? Where is Noman? He left. What's the answer, people? Ira, Kaval, Ahmed. Yeah, all of them are alcohols except this. This is an acid. It's propanoic acid. This is an alcohol. This is an alcohol. This is also an alcohol, right? Because, I mean, doesn't matter if it has 2 or 8 functional groups, it's still an alcohol. It'll do all the reactions an alcohol can do. This won't do any reactions an alcohol can do because it'll do acid reactions. The OH behaves differently because of the carbon with the oxygen double bonded. So all 3 of these are alcohols. This is called a diol because it has 2, right? Did you guys know, like Panadol, when you say Panadol, the OL in Panadol signifies that it's an alcohol. There's an OH attached to it. In the molecule of Panadol, the organic molecule. Now, Panadol is a generic name. The actual chemical name for Panadol is, I think it's paracetamol, that's what they call it, but like the actual molecular name, it'll have like butane something, this type of naam hoga uska, and that all implies that. And that's the functional group. Yeah, makes sense. C is the answer. 4 is not. So 1, 2, and 3. Which alcohol on oxidation will produce this? Looks like propanoic acid. You can also name this without, drawing it out. It's propanoic acid, 3 carbons and an acid. What do you guys think? Propanoic acid. This is propanol. 1, 2, 3. This will do it. Right? Funnily enough, you'd think it would be this because the product would be bigger, right? What's happening over here is the carbon, the final carbon loses the 2 hydrogens and gains another oxygen. So the oxygen, instead of writing it like this, they've written it 2 karke. So this molecule looks a little small than this one, right? And that illusion makes you think that, oh, it can be C because this is a bigger molecule. How could a bigger alcohol give you a smaller acid? But just writing it this way makes it look big. Otherwise, these 2 will do it. So C is your answer. I hope that made sense. I could repeat it if you want. How many of the following statements about ethanol are correct? Ethanol is CH3, CH2, OH, that's C2H6O. So this is correct. Manufactured from ethane and steam. Ethane cannot undergo reactions. Ethene can. This is wrong. Oxidizes to ethanoic acid. Why not? Overall, no, you have to tell the total number of correct answers. So our count is up to 2 right now. Produced by fermentation of glucose. Yeah. Ethanol, right? Yeah. Used as a fuel, used as a solvent, something I didn't discuss, but ethanol is a good solvent. All right. So how many are correct? Looks like 5 are correct. No. Yeah, 5 are correct. So C. Only one statement is wrong. Number 2. Easy? Thumbs up if easy. Thumbs down if hard. All right. Yeah, I think this is good. Let's go back to alkenes. Now, alkenes might be a little different because that had the most chemical reactions. If you remember alkenes reactions, which row is correct for the reaction of alkenes with steam and catalyst? C. So it's, if you can imagine it in your hand, great, but it's better if you draw it. Steam as a catalyst. Now, A, if it gets produced, is going to be so they're saying the double bond will go away when you add steam to it, and it'll form over here. This is correct. And the other one will come over here as hydrogen. So this molecule is correct. But however, the OH can also be connected over here. What's stopping it? So the reverse is also true. So another molecule will be produced, which will be like this. CH3, CH2, CH2OH. And it's not only, right? So this is wrong. A is wrong. They're not talking about the only one. Same issue over here. You'll have an OH at the end, sure, but you can also have an OH joined over here, which is not only then. This is out. C is interesting. It's pretty cool to look at C, which is CH3, C double bond, CH3, and an H over here, and an H over here. So let's say we put the OH in the first one, and the H over here. Take it. This is the molecule. Let's just clean it up a bit. This is the molecule. Now what could happen is the OH and the H can be attached to it the other way, which is the OH can go over here. Like right? So the idea is, isn't this molecule and this molecule the exact same molecule? Why do I say that? Let's say if I flip this molecule about this line, this entire part would here, like, you know, like that. If I do that, I'll turn it into this molecule. So these two molecules are this, the same one. So however way it is written, it will only form this, only because it's symmetrical. That's pretty cool this way. And D has the same issue, right? So C is your answer. All of these will be produced, but they won't be the only one. Only because of C, because of a geometrical, you know, coincidence. Its reverse is also similar to the first one. So it will only form that because, yeah. All right, question number 2. When butene reacts with bromine, which compound could be made? Now, what's important over here is, I'm not too sure why people get confused with this. It's kind of, maybe the question is like, what are you talking about? Or people think it's trying to talk about something else. So if you have like a alkene like that, the double bond opens up from here. Right? So this carbon can now carry one other atom or make one other bond, and this carbon can make one other bond. So what happens when bromine reacts is the bromines connected are always adjacent to each other, right next to each other. Now, sometimes you can see it like this, that they'll make the bromine instead of here, they'll make it over here, but that's the same thing, right? That doesn't really matter, but they will be next to each other. So they won't be on the same carbon. That's wrong. That can't happen. That means one carbon somehow ended up getting two other bromines. How would that happen? This is correct, because this is essentially what we've drawn. Over here, there's some space in the middle. That cannot happen. And there's too much space over here. This cannot happen. The correct answer is B. Yeah, let's do 2 or 3 more questions. Let's call it a day after that. Which statement about hydrocarbon C2H4 is not correct? It contains a double bond. Well, it does have a CN H2N. It's matching that formula, or you can just draw it out. 1, 2, 3, 4. If you have 4 carbons joined to it, there must be a double bond over here, right? Because otherwise you'll need more hydrogens. It contains a double bond. It will decolorize aqueous bromine because it has a double bond. It forms condensation polymer. That's not true. It forms an additional polymer. It doesn't make water. No, I think it's just called addition polymer. It forms an alcohol when reacted with steam. That's also true, right? How can alkenes? Let's skip this for now. Question number 5, which statements are not correct for alkenes, but not for alkanes? Which statements are correct for alkenes, not for alkanes? They'll turn aqueous bromine from brown to colorless. They're true for alkenes, but not for alkanes. This is true for alkenes and not true for alkanes, right? They burn in air to form carbon dioxide. Both of them burn in air. So this is fine. This is fine. This is something we don't want. So 1 and 2 is the best answer or the only answer. 4 hydrocarbons are shown. Which row is correct? Are they isomers of each other? W and X. Are they isomers of each other? They look like isomers of each other. They're different structures. Do they have the same molecular formula? W has 4 carbons and 10 hydrogens. X has 4 carbons and same molecular formula, different structures. This is true. Y and Z will decolorize aqueous bromine. Well, it has a double bond. It has a double bond. So yeah. W and Y are branched. W and Y are branched. Yeah, so it's like branching when they're not in the carbons are not in a straight line. So that's true. So that easy, or A is just correct. Yeah. So over here it's saying X and Y are branched. X is not branched, so this is wrong. C, Y and Z, I'm just checking what's different from the answer so we can highlight quickly what's wrong. Y and Z are isomers. Y and Z. Are they isomers? They might be isomers because this is a straight chain, or they might look like it, but this is C4H8, I think, and this is C3H6. So their molecular formulas are different. Doesn't matter structure, the molecular formulas are different, so they're technically different molecules. This is out, and this is out. So A is our answer. Glad we found it early on. Otherwise, this question would have taken double the amount of time. Pretty cool. Which substance will react with ethene? The ethene so far is the most reactive of all organic molecules. So it's kind of crazy because I think we did 5 reactions with it. It cannot react with argon because that's a noble gas, but it can react with hydrogen. It can react with oxygen. It can react with steam. So an alkene reacting with a hydrogen turns into an alkane. That's also called reduction. This is combustion, just burning, right? With steam, it turns into an alcohol. So all of these reactions you've seen. So A is your answer. Oh, more than one product, sorry. So over here, it forms one product, right? Over here, it forms carbon dioxide and oxygen, water. So that's your answer. I misread the question. I thought, which won't it react with? With alcohol, it forms only one product, right? Like with the steam, it'll only form ethanol. Like that, not showing the hydrogens. All right, 8. The diagram shows final question. The diagram shows the structure of two hydrocarbons, X and Y. Two students make the following statements. X and Y are isomers of Y, and hydrocarbons X is unsaturated, but Y is saturated. Well, let's look at the second one first. Is X unsaturated? X is actually saturated because it doesn't have a double bond. This is unsaturated. So ulta kara, right? This is wrong. Student 2 is, yeah, student 2. Student 1, they do look like isomers, but the problem is, again, they don't share, I think, the same molecular formula. How do I know? Well, one has a double bond. So if this is C4H10, I believe, right? The one on the right is C4H8. They don't have the same molecular formula, so they're not isomers, they're just different things. Neither are right. Yeah, let's end it here. I'll see you guys next class now. But Era and Noman isn't here, but Era will continue in a bit. Okay, chalo. Kawal, thanks for joining. See you. Bye-bye. Yeah, see you guys.